Alright, so we are now going to discuss the general case for a stoichiometrically balanced equation. So by general case, what we mean is that if we write the equation as nu A into A plus nu B into B is going to nu C into C plus nu D into D. Now the question is, what will be the most general form of the reaction quotient and the equilibrium constant for this reaction? Now, as before, you can write it as the dg, or the change in Gibbs free energy. We are not writing the minus SDT plus VdP term, so we are right away writing the constant pressure temperature term, and that will be sum over all the constituents I, and that will be nothing but mu I dni, something like we started with. And dni, we know that it has to be multiplied by the stoichiometric number times the, we can just write it, introduce another step. So this is nothing but nu I. And remember, when I am writing for A, it will be minus nu A because we have to include the sign. Because it is being consumed, into xi. Xi was the advancement of the reaction. So we can write it as, for a differential amount, it will be nothing but mu I, nu I is a constant, into d xi. So that we can actually write that this sum, remember d xi doesn't have any index because it is independent of reactant or the product. We can write it as mu I, this sum times d xi. So we can actually take now the derivative of Gibbs free energy at constant pressure and temperature, and we called it as the reaction Gibbs free energy, and that will be nothing but sum over I, nu I, and we write it as mu I into nu I. And we already know that what is mu I? Mu I is nothing but mu I 0 plus RT ln activity of that species. So I'm writing the nu I term at the beginning, and then I'm writing it as mu I 0 plus RT ln activity of I. Now if we write it in this way, see the beauty here. So and now I am going to expand it just to or before expanding it, we can also write it in terms of just the summation notation. So you see here that I can actually write it in two different terms. One is basically sum over all the mu I zeros, and the other one is basically sum over the RT is a constant. We can actually keep it outside, and we'll have nu I ln AI. Now we already know what is ln AI, and ln AI, if I just write the notation, let me just write it here. So what is ln AI? Nu I ln AI. What is, say, A ln x? That we can write it as ln x to the power A. That we know. So that way I can actually use this factor nu I and as an power of the logarithmic term. So we can write it as nu I, mu I 0, or let me just use the next line. We can write it as sum over I, nu I, mu I 0 plus RT, and then sum over I ln AI raised to nu I, and then we are summing up. Now what is the sum of ln? Sum of ln means, what is, say, ln x plus ln y? It will be nothing but ln xy. So it is basically taking the logarithm of the product terms. So that we can write it further. And in this case, there was already a power here. So x was raised to say a and y was supposed raised to b. So it will be something like x raised to a, y raised to b, something like that. So we can write it as mu y 0 plus RT and ln of product of all these terms nu I ai to the power nu I. So that is our equation, and that is basically the reaction Gibbs free energy expressed in terms of the reaction and all these activities of the reactants and the products. Now this, if you now remember that delta G of the reaction was nothing but the first term will be delta R G 0, so that we can always equate, and this will be nothing but RT ln Q. So you can see what is the expression for Q. Q is not just for the general equation which we had for a specific equation which we considered like AB, we wrote it that time Q is partial pressure of B divided by partial pressure of A, but now we are writing it in the more general sense, in the sense that we are writing it as Q is nothing but sum over, or we can just write it in this way, Q is nothing but so it was RT ln Q, so it is sum over AI to the power nu I. So for example, for the reaction which you wrote, for that it will be nothing but, first think about the reactants which was nu A, so we can write it as activity of A raised to nu A, but there was a negative sign, remember. Then activity of B, similarly this was reactant, and similarly activity of C, this was product, nu C, and activity of D, that was also product, and that's why we have to take the positive sign. So we can write as nu C activity of D nu D divided by activity of A nu A activity of B nu B. So this is the reaction quotient. So we see that we have to take in the numerator all the activities of the products raised to their concentration and all the and then multiply all for each product divided by the same for the reactants. Now you see a very interesting situation. If we can actually write in terms of the activity, we can write partial pressure also, but for this general equation, when we wrote as A to B, so we wrote that it is basically PA by PA0, or PA0 doesn't make sense, it is basically divided by P0 because P0 is same for everything, and divided by PB by P0, and that P0 actually got cancelled, and that's why you wrote it as PB by PA. This should be PB by PA. However, you see that if we want to write it in this way, I will have actually pressure of C divided by, or we can actually think about, you can just modify this equation a little bit. Let's say that we write this equation as nu A into A is going to nu B into B, and this is the stoichiometries are not equal. Then I'll have a very interesting situation. I can write the activity of B divided by activity of A, and then it has to be raised to the exponents B and A here. So what we can write actually is PB by P0. We have to always take the PB divided by P0 because it's a standard state notation, raised to nu P divided by PA by P0 raised to nu A. So if the nu A and nu B are not equal, then I cannot cancel the P0 terms, which is here. So that's the importance of the thermodynamic equilibrium constant. It is not just Pb by Pa or the concentration of B by A in the dilutes case. You have to take the division by the standard state, and then you have to take the exponent. You have to take not the exponent, you have to take the power. So these P0 things do not necessarily cancel out. So we can say that Q is this, and then what will be K? And already we know that K is nothing but the equilibrium constant. We wrote it as K equilibrium. So K will be the same activities but at equilibrium. So Q is the general activity for any condition, and K will be nothing but the same thing but at equilibrium. At equilibrium. So that's how we can actually explain K and Q. Now this question is, how will I write the activities? So we wrote that we already discussed the activity can be expressed as activity coefficient times the mole fraction, but not for not always actually, but for say dilute solution we can write it, or sometimes you actually write it in terms of molality also, where you write it as say it is the activity coefficient times the molality, which we write as Bi, divided by the standard state. Always you have to keep that in mind. Or in terms of pressure, we write it as pressure of the constant I divided by pressure of the standard state, which is just 1 mole per 1 bar. And in the very dilute concentration, instead of the molality, we could also write it. So we know that for dilute concentration it will be nothing but Bi by B0. Similarly, we could also write it as Ci by C0. So if I express this activity in terms of pressure, then the corresponding equilibrium constant is known as the equilibrium constant with respect to pressure. We write it as Kp. If we express it with respect to concentration, we write it as K suffix C. And of course there is a relationship between Kp and Kc. You know that you can actually write it. It won't be actually equal. You can actually write it in terms of something, and then you can actually figure it out, what will be the relation between Kp and Kc. Already you know the relation. How to get you have to write the pressure in terms of concentration, and then you will easily figure out what is the relationship. However, the point here is that there will be some P0 terms or the C0 terms that will not cancel out. So because the addition of all the nu C, nu D's, and the addition of all the nu A, nu D's, and when you take the difference between those addition, which we sometimes write it as delta N, which is nothing but this sum, basically nu D plus nu C minus nu A, nu B, which if it is not equal to 0, then the pressure terms do not cancel out, or the concentration terms, the P0 terms, or the nu C0 terms, they do not cancel out, and you have to keep that in mind. So we are actually dividing it, pressure divided by 1 bar, so that we make it as unitless. So you express the pressure as bar, and then divide by 1 bar means it's just a number. And similar thing is also for the concentration or for the molality. You can actually easily convince yourself that it is just a number, but not something that we have to think about. Like we have to, it's just you have to treat it just a pure number. Now the thing which we are going to discuss in the next section is how this equilibrium constant gets affected by change in pressure or change in temperature, or what are the contributions of the external disturbance in terms of pressure or in terms of temperature. So that we are going to discuss in the next section.